part of 7.5, we had several sum and difference identities we talked about yesterday. We did the sine and the cosine ones pretty in-depth. Okay, we went through lots of examples. I didn't do a lot with the tangent ones. Okay, so we're gonna look at that more today. That's the tangent of a sum. Now, that's not an identity that I normally memorize off the top of my head, but I do know the sine and the cosine. So what I want to do is, I want to pretend that I don't know this, and I want to figure it out. Okay, I need to figure out the tangent one. I need it, and all I know is sine and cosine. How can you rewrite tangent in terms of sine and cosine? Yeah.
You can have sine over cosine
Right.
with the same insides as the tangent.
Yeah, just keep the argument the same. Whatever the argument is, change it to sine over cosine with the same argument. So this requires me to know the sine of a sum, and it requires me to know the cosine of a sum. Okay, so let's write that out. Okay, what's the formula, or just the template for sine of a sum? Just tell me the trig function. Something, 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 something.
There's
Sine of something and cosine of something.
Sine, cosine,
Plus cosine.
sine. Yep. So it's sine, cosine. Keep the symbol the same. Cosine, sine. And then you just fill it in 1, 2, 1, 2. Alpha, beta, alpha, beta. Beta, alpha, beta. Okay. Now, what's the template for cosine of a sum? Yeah?
Cosine, cosine,
Cosine, cosine.
minus
It's got to be the opposite.
sine,
Sine, sine. And again, you fill it in 1, 2, 1, 2 for your angles. Okay, now, when I look at that, it does, what's in black there doesn't look anything like what's in that red box. So, I'm looking for suggestions at how I could turn this into that. Yep.
Which, sorry, whichever has like the same argument, you can turn into tangent. So like sine and cosine, if their argument is both alpha, you can turn into tangent.
So I'm not sure like what operation. So like what are you looking at? Like I'm trying to figure out what you're doing mathematically.
So like sine with the argument of alpha, cosine with the argument of alpha.
Yep.
Could I turn it into tangent?
Oh, are you trying to like split this problem like into two problems?
Yeah.
So when you have a fraction, like let's say you have something in the top, something like that in the bottom. Actually, that wouldn't work. Let's try it. If you want to split that into two fractions, look at this one.
The same denominator.
Yeah, you could do x plus, you could do, how could we do that? Let's do x over z plus y over z. Okay, that's the rule. You can take each part of the numerator and put it over the same denominator. So what you'd have to do here is put this over all of that. And then you could put this over all of that. We could try that. I don't know how messy that's going to get.
Yes.
But you have to take the first part of the numerator and put it over the whole bottom, and then the second part and put that over the whole bottom. I mean, it would probably work. I have an easier way to figure that out. Yeah?
Can we turn the bottom into cosine squared out zeta minus, like get it simplified somehow?
No, these aren't like terms because this is an alpha and this is a beta. So you can't multiply this cosine times that one because they're different. Okay, but if you focus, look at the numerators. How many terms are in the numerator in the red box?
2.
2. How many terms are in the numerator for what's written in black?
4.
Remember, terms are separated by plus signs and minus signs.
Oh, 2.
There's only 2. Okay, how many terms in the red box in the bottom?
2.
There are 2. How many terms in the bottom of what's written in black?
2.
There's also 2. So there's 4 terms altogether. There's 2 in the top, 2 in the bottom. So let's just kind of put boxes around them. What does that term correspond to and what's above?
Tangent alpha.
Corresponds with tangent alpha. Okay. What does that one correspond to? Tangent beta. Okay. What does that one correspond to?
1.
1. And then the minus we have right there. And what does that correspond to?
Sine alpha, sine beta.
Sine alpha, sine beta. Okay, so that's what they correspond with. I would like to change one of these ones in the bottom so that it matches one in the top. What do you think the easiest box to work with would be? The black, the red, the green, or the blue?
The green.
The green, yeah. The green one is the easiest one to work with because it turns into something that's a 1. So how could you turn this green box into a 1?
Is there a double angle identity?
No, it's more of just something you can do arithmetic-wise to turn any number into 1, or any quantity into a 1. Yeah?
Oh, what's it called when you like multiply it? I just can't find the word, but they try to cancel like what you do on the bottom and put it on the top.
Yeah?
Divided by itself.
Divide it by itself. Whenever you divide something by itself, it will turn into a 1. Now, if you do that, whatever you do to the green box, you have to do to the black, the red, and the blue. You have to do it to all of them. So, what could we divide the green box by? Don't say itself. Like what could I actually divide it by?
Cosine beta and
Cosine what?
alpha.
Alpha.
And cosine beta.
Cosine beta. So we're going to divide everything in those boxes by cosine alpha, cosine beta. So let's write it down and see what that looks like. So we've got sine alpha, cosine beta. We're going to divide it by something. Plus cosine alpha, sine beta. We're going to divide that by something. Then we're going to have the original division line. Cosine alpha, cosine beta. And divide that. And sine alpha.
There's no subtraction.
Yeah, I'll fix that. Thank you. And we're going to divide that. Okay. So all 4 of those things are going to be divided by cosine alpha, cosine beta. Let's write that down. Cosine alpha, cosine beta. Cosine alpha, cosine beta. Cosine alpha, cosine beta, and cosine alpha, cosine beta. Now, I don't know what's going to happen to all the other boxes. My only goal was to turn this green box into a 1. And I hope by doing that, everything else just magically comes out to what it needs to be. Okay. So what can I do here? Let's look at each one of them one at a time and see if there's anything we can do. Yeah?
You can cancel the cosine betas
Yep.
with each other and then turn the sine alpha over cosine alpha into the tangent alpha.
Yeah, so let's worry about doing all the conversions after. Let's do all the canceling we can first. But yes, exactly. What about in the second one? Anything that cancels there? Cosine alpha. What about in the third one?
Everything.
Whole thing.
That's not going to cancel.
Nothing's going to cancel that. Okay, so now, these are the same argument. What's the sine of alpha divided by the cosine of alpha? That's tangent alpha. Plus, these are the same argument. What's sine beta over cosine beta?
Tangent beta.
Tangent beta. Everything canceled, so what are you left with there?
1.
1 minus. Now, you have, think of this as that and that. We just did that.
Times tangent beta.
Sine alpha over cosine alpha is tan alpha. And what's sine beta over cosine beta?
Tangent beta.
Tangent beta. That is the identity we were trying to get. Tangent plus tangent over 1 minus the product. Tangent plus tangent over 1 minus the product. So that's a trick that you can use a lot. If you have two things that you know are supposed to be equal and you're trying to make them look the same, don't focus on making the whole thing look the same. Just try to make part of it look the same, like the green box. And usually if you can make that look the same, other things will start to look the same on their own. Any question on that? Yes?
Sorry to ask, but how does that work, the splitting the fraction into the two parts and then...
Into two parts?
Yeah.
Well, it's just like if I had 3 times 5 over 12 times 20. I can split that in half and treat it as 3/12 times 5/20 because it's multiplication. And then I can reduce this separate. And I can reduce that separate. And that's what I did up there.
Oh,
You can reduce each one separate.
thank you.
Yeah. So a lot of the properties you know with numbers, simplifying things, distributive, quadratic formula, all those properties can be applied to trig. But it requires you to really understand what you're doing when you do it with numbers if you're going to do it with something like this. All right, so these, I'll just put them up again in case there were any that you didn't get. These are the double angle identities. Again, the two most important ones, if you know this one and you know this one, you can figure out anything else you need. Okay, these other two for the cosine, they come from sine squared plus cosine squared equals 1. I think I showed you that yesterday. And this one, I don't know if I've ever done it, but I'm sure you could figure it out by doing sine 2 theta divided by cosine 2 theta. And you could derive where that comes from. No problem. Does anyone have any questions on those double angle identities? Again, I had them all on the board yesterday. That's not anything new. So if you wrote them yesterday, you don't have to write them again. Let me just see. Well, let's take a second and look at this tangent 2 theta. I don't know if I've ever tried to figure that out. How can we write tangent 2 theta instead of writing it tangent 2 theta? Yeah.
Let's start off by turning it into sine 2 theta over cosine 2 theta.
Okay.
And work from there.
So sine 2 theta over cosine 2 theta.
You can use the identities to those two ones from above, and
Okay. So let's do, what's sine 2 theta?
2 sine theta cosine.
2 sine theta cosine theta. Okay. Now,
There's another one.
the bottom is cosine 2 theta. I have 3 choices. I'm trying to get something that looks like this. Which one of the 3 looks most similar to that one?
the best idea would be the second one. The
Yeah,
one right in the middle.
maybe the middle one, because we're looking for something with a 1 right there, and that already has a 1 right there. Maybe. Let's just try that. 1 minus 2 sine squared theta. So that is the formula for tangent 2 theta, but somehow that simplifies to that. So, oh, I forgot the sine squared. Sine squared. Okay. Right, and I got a 2 there, and I got a 2 there. I'm not sure if that's going to help me somehow. Any thoughts on what we could try to do? Yeah?
Dividing everything by like sine, and dividing everything by cosine theta, because then it cancels out.
How about
Well,
How about dividing everything by cosine squared? Because if I divide everything by cosine squared, I'm going to mess this one up, so that concerns me. I'm not sure what's going to happen with that. But if I divide everything by cosine squared, it's going to make the top exactly what I want. Okay? So I like the idea of dividing and using cosine, but let's try cosine squared. Okay? Watch what happens. So we've got 2 sine cosine. Let's divide that by cosine squared. And let's take the bottom and divide it by cosine squared.
On test, what would you recommend to be the best method to do multiple fractions in a fraction to show them?
I write it just like that. Okay. So I took top and divided by cosine squared, and I'm taking the bottom and dividing by cosine squared. Okay.
The cosine squared will drop it out to 2 tangent because
Right, what's going to cancel in the top?
it's going to cancel with the cosine, turning the cosine squared on the bottom just to cosine, and then
Right. Can cancel 1 cosine from the top, 1 cosine from the bottom. Okay? So now you're left with 2 sine over cosine. And what is sine over cosine? So I have 2 tangent. So I've got the top exactly the way I want. Okay? I don't want to mess with the top anymore. But let's see what the bottom looks like.
the bottom.
What trig function do you get when you flip cosine? You get secant. So what function do you get when you flip cosine squared?
Secant squared.
Not thrilled with that. Okay, we get secant squared. But we also have sine squared over cosine squared.
Tangent squared.
That's 2 tangent squared. So let's go back up and see what we have. Okay, we've got the 2 tangent. That's good. And the bottom is supposed to be 1 minus tangent squared. And we have secant squared minus 2 tangent squared.
Well, if we were posting this on the denominator, you would just divide by tan, I think.
Well, if you want to divide something in the bottom, we now would have to do it to the top, and that would mess the top up. So we've got the top exactly the way we want it. So what I think we need to do to the bottom is some kind of substitution. We've got to change something that's there.
Let's change the tangent over to the sine squared and cosine squared, and the.
Let me give you a hint. I think I know what we need to do. This kind of looks like a Pythagorean identity. It's not, but there is a Pythagorean identity that has these in it. That's my only idea, is to substitute in and see what happens. What's the Pythagorean identity that has tangent squared and secant squared? Yep. 1 plus tangent squared equals secant squared. If that doesn't work, I'm not sure what we're going to do. That's my only idea.
Oh.
What trig function do we have in the bottom here that doesn't appear in the identity? What trig function do we have in the bottom that doesn't appear in what I have circled right there? Yeah?
Secant?
Yeah, I don't have any secant. So then I would get rid of that. I would use the Pythagorean identity. What can you substitute for secant squared? Yep.
By replacing secant squared with 1 plus tangent squared.
Right, let's do that and see what happens. I need to see it so I can see what's going on.
We would
So 1 plus tangent squared.
minus 2 tangent squared. The 2 and the tangent squared.
So yeah, we have the 2 tangent in the top.
The tangent squared on the bottom and the 2 on the 2 tangent squared would cancel, leaving you with 1 minus tangent squared.
Yeah, so these are like terms. This is 1 tangent squared, take away 2 tangent squareds. 1 take away 2 is negative 1 tangent squareds. So we have 1 from right there. And then 1 minus 2 is negative 1 tangent squared. And let's see if that's what we were supposed to get. Yeah, exactly. That's the first time I ever tried to prove that one. I don't know if that's the best way, but it definitely worked. And overall, I mean, it wasn't, I don't know, maybe it was like 4 or 5 steps. If it starts to get into like 10, 15 steps, then I know I'm probably getting into something that could be simpler. Okay, but if I can do something for this level of problem in about 5 steps, that's good. Okay, and if you can think like that to figure out that identity, then you really understand how to work with identities well. That kind of thinking, it just doesn't come automatic. It takes time. Yeah.
I think if I had all the trig identities like on like a sheet, then I'd be able to do that. But like I would not remember that 1 plus tangent squared is secant squared.
Yeah, so that's a Pythagorean identity we did last week. So if you could at least do it with that written down, that's good. And again, that's an identity that if you didn't know it, you could figure it out. So that's the thing. If you forget them, you can always work backwards and figure them out. It just really starts to slow you down. And then you lose track of what you're doing. So it's like you're trying to put something together. You don't have the right tool to build what you're trying to build. So now you stop building that and you make the tool you need to keep building. And then it starts to slow you down. Okay, but you can do it. All right, so let's try a couple of these. This one's pretty similar to the homework. It says to rewrite 2 cosine x plus sine 2x using only sines and cosines. So the idea is I don't want any 2's inside the argument. Okay. Out of those 2 terms, which one of them is okay the way it is? Yeah.
The 2 cosine x is fine.
2 cosine x is fine.
Replace the sine 2x with be 2 sine times cosine x.
And if that's all they said to do was rewrite in terms of sine and cosine, at that point you've done it. Now, if they said to rewrite it with sines and cosines and factor it, okay, this is where now we're going to start to tie in some factoring. What can you factor out of this term and that term?
You can factor out the 2, so you have
And you can also factor out, the cosine of x. Yep.
yeah.
If you factor out 2 cosine x from the first term, what do you have left? 1. And what if you factor out 2 cosine x from the second term? Sine x. That's a factored version of the answer. Why is the factored version helpful? Because if I was going to set this equation equal to 0 and now solve it, you set each one of these factors equal to 0 and get x by itself.
So-
That's where we're going.
So the left side would just be cosine x would be equal to 0 because of its multiplicational there.
Right, it would end up essentially being cosine x equals 0 and 1 plus sine x equals 0. And now you're going to get x by itself in both of those. So when you're starting to get x by itself, now that's going to tie in something we've done before too. We have to tie in the ASTC diagram. Okay, so all these things are kind of starting to come together. All right, but for this one, I'm not going to solve it. I just wanted to get it to either this step or this step. They're both correct. Let's try it on this one. So this one does say to solve. What I would like to at least do first is get rid of these numbers. And then if we can solve it, well, we can try to. Okay, so I modified it a little bit because we can do it with a 2 and a 3, but it's just going to end up getting kind of messy. So let's do it with a 2 and a 1. Okay, again, the goal, you can't have any numbers next to x. So we don't want that cosine 2x there. Now, cosine is one that we can use. There's 3 different formulas to get rid of the 2. Let's go back and look at the 3 formulas. We're going to get rid of this. This is going to stay right where it is. So I already have a cosine in the problem. If I could keep this problem to just having cosines, I would prefer that. Okay, I'd rather have just one trig function than 2 different ones. So let's look up cosine 2x and see if there's a way we can rewrite it with cosines. So is there a way I can rewrite cosine 2 theta with just cosines? Yeah?
2 cosine squared theta minus 1.
Yeah, I would use this one. That way at least I'm keeping the just cosine in the problem. And I'm not mixing in sines and cosines. Okay, so 2 cosine squared theta minus 1. Okay, so let's start with that. And we're going to solve it. Okay, we're going to set it equal to 0. I thought it said, yeah, solve for the zeros. Now, let me reorder that. Okay, it kind of looks like something I'm hoping you recognize. Oh, actually, does it look like anything before I reorder it? Yeah?
Can't you move the...
Yeah.
Is it called trinomials? Where it's
It is a trinomial. It's a special trinomial. It does have 3 terms.
quadratic?
It is. That's a quadratic equation. The way we know it's a quadratic is because quadratics always have 3 terms. And the term that you have in the middle, whatever power that one's raised to, you have to have the same power here, but doubled. Okay? So this is cosine to the first, that's cosine to the second. So solving this problem is going to be just like solving this. If you can solve the bottom one, you can solve the top one. It's going to be the same thing. This, I mean, it's okay if you want to think of it like that in your head, but I really want you to think of it with cosines. Okay, that's the same thing.
Shouldn't we replace the theta with the x?
Oh, yeah, I'm sorry, I need to be using all the same letter. Yeah. So I used x's at the beginning, so I should be using x's in this problem. Okay, what's one way that you can try to solve a quadratic? Yeah. We could try the quadratic formula. What's another way that we could also try? Yeah, just to start out, let's try it with this and see if we can factor it.
We know that one of them needs to be a minus while the other's plus.
Okay, so we do need a minus and a plus. What about the first term in each?
One of them needs to be like 2x while the other's just an x.
Mm-hmm.
But we've got to be careful about whether we have the 2x in the plus area or the minus area, because that could change some things around.
Right, we might have to switch the plus and the minus. But what about two numbers that multiply to give me 1? Yep.
1 and 1.
1 and 1. Let's see if that works. That gives me 2x squared minus 2x plus 1. Is minus 2 plus 1 what I have in the middle?
Yes.
We have
Negative 2 plus 1 would give me 1.
No,
That would be
I thought you
negative.
were talking about negative ones, because like constant.
So what do we have to do to fix that?
We've got to swap the sign.
Yeah, I just swapped the signs. Let's try it this way. Now we get 2x squared plus 2 minus 1. What's 2x minus 1x?
1x.
1x. That's exactly what's supposed to be in the middle, and negative 1 times 1 is negative 1. So we factored it.
So
But we need to factor it with cosine, not with x.
can't we just replace the x with cosine
Yeah.
x?
So what this really factors is 2 cosine x minus 1 and cosine x plus 1. But you never would have been able to factor it if you didn't know the double angle identity for cosine 2x. That was the point of this problem. You had to know the identity that we learned in this section. All right. Now, what do you do with each of these factors? Yeah, set them each equal to 0. Okay, I'm not going to go too much further than that because now it's starting to get into what we're going to do tomorrow. I just wanted you to see how you could use a double angle identity to get this to a factorable point. So I've kind of done what I wanted to show you. But yeah, you'd set them each equal to 0. And now you would get everything on one side and you get x on the other.
Well, you have to use inverse cosine.
Yes. Because you're going to add the 1 and then divide by 2.
And then inverse cosine.
And there you just subtract the 1. And now you need to take the inverse cosine. But I'm going to stop there because that's what we're going to do tomorrow.
Oh wait, so you want, for tonight's homework, you want the final answer, you just say cosine or sine of x equals that.
Yeah, I think in the homework, as far as they're going to have you go, is like up to this step.
Okay.
Taking something that had a 2 in the argument, getting rid of it, and then just factoring it. And the reason why is so tomorrow we can solve it.
That's true.
Any question on that? At least just up to the factoring?
You mind going up real quick? Shouldn't we graph this? Because it would be I think there would be more answers than just.
Well, there's going to be. Let me think about it.
Plus,
Cosine is positive.
the right one wouldn't work.
So you're going to get
Pretty sure.
1, 2. You should get 3 answers if you graph. So if you graph this, it should cross the x-axis 3 times between 0 and 2 pi. Okay. We can check it real quick. I don't want to spend a ton of time because this is tomorrow's stuff. Cosine of x squared. I think that's how I want to type it. Yep. Was there a 2 in front? Yeah, 2. And then minus 1. And then plus cosine x.
And then the 2 zeros, or?
I need to set my window first, 0 to 2 pi.
Oh, that's what it means.
Yep.
I thought it said to solve for this or something.
So I predicted 3 times based on what we did. So there's 1. There's 2. There's 3. Perfect. So the work that we did confirms exactly what you're seeing graphically. Tomorrow you could graph it if you want to check, but we're not actually going to use the calculator to really do anything tomorrow. We're going to do everything algebraic. So factoring in quadratic form.
What'd you put for the?
I just typed in the original problem. 2 cosine squared x.
It doesn't look the same as.
If you type exactly that, it'll look like that. I have to see what you have that's different.
It might be the y. I have.
Yeah, it could be the window. I mean, if you change the y, it might look.
I have it from -4 to 4.
Yeah, so yours is going to look a little more stretched. Mine's going to look more squished.
How come on the graph there's 3 answers but algebraically you solve 2?
Because you're going to get 1 answer from this, but cosine is equal to positive 1/2 in 2 different quadrants. Cosine is positive in quadrant 4 and quadrant 1. So you get 2 answers here, 1 answer here. And if you're like, well, wait, why don't you get 2 in this one? It's because -1 is on an axis. So when you're on an axis, you don't even use this diagram. This only applies to this part of the problem.
Does it? Wait, are you saying it only applies to fractions, or?
Just when you have a number that's not when it's in a quadrant. 1, -1, and 0. Those values are not in quadrants.
The other number is pi.
Yeah.
Pretty sure.
Oh, okay. Yeah.
There's, and it's. I don't think there's.
Okay, because think about the graph of cosine. You draw it, it looks like this. Okay. 0, 90, 180, 270, 360. It hits -1 at 180. 180 is not in a quadrant, it's on an axis.
Oh, okay.
When it's on an axis, this diagram doesn't apply. But again, we're going to get into more of that tomorrow. Okay.
It doesn't work for the angles, from what I know.
All right, so we know how to figure out on the unit circle angles that are multiples of what numbers now. We used to just be able to do the 30s and the 45s, but now we can add in the what?
15.
We can add in the 15s, right? Because we have the sum and difference formulas. Well, if you can do an angle, technically you can always do half of that angle. And the way you can do half of it is with the half angle formula. These identities, if you ever needed the half angle ones, I would give them all to you. Okay. So as far as memorizing half angle formulas, I would not worry about memorizing them at all.
That's complex.
Yes. But let's say I wanted to figure out, well, even like this. Let's say I wanted to figure out the cosine of 15. How did we figure out 15 yesterday? Yeah?
Like 45 minus 30.
Right. We treated it as a difference problem, which is fine. You can do it that way. You can do 45 minus 30 as long as you know the cosine difference identity. Now, let's say you didn't know the cosine difference identity. and you wanted to figure out 15. Then you want to have another guess at how you could write the number 15 using an angle that we know. Yeah?
30 over 2.
Yeah, you could do 30 over 2. Now yesterday that wouldn't have helped at all because we didn't have a formula we didn't have a formula for when you had a 2 in the bottom. Now you do. So if you wanted to figure out the cosine of 15, you could do it this way. The square root of 1 plus the cosine of 30, and then divide by 2. So it gives you another way to do it. Same thing with sine. If you wanted to figure out the sine of 15, and you didn't remember the difference formula, but I gave you this one because I wouldn't expect you to memorize this one, you could use that. Okay, we'll try it. We'll try doing like the cosine of 30. We'll do it the way we did yesterday, and then we'll try it with this and see if we get the same thing. And of course, we always have the tangent one, but you could just do sine over cosine if you had to. But that's the tangent one.
Wait, so you're just adding 1 to the bottom? Or having...
So for the tangent one, it's the sine of theta divided by 1 plus cosine. Again, to see why these make sense, we probably have to go through and prove them, which I'm sure we could do. But
I'm pretty sure
we've
the
proved
tangent-
enough. I don't really want to spend too much more time proving these.
I'm pretty sure the tangent one would take too long to prove.
Yeah, I just want to try, let's do the cosine of 15. Well, we could do sine of 15. Anybody care which one we do? But let's do cosine 15. Okay, let's do it as a difference, so we can get our answer, and let's compare it to what happens when we use this formula. Okay, can someone give me the whole formula for cosine difference? You go ahead and fill in what you need to. Yeah.
Cosine 45, cosine 30, plus sine 45, sine 30.
Yep. Okay, let's go through all of them real quick. Cosine 45. Let's do 2 over 2. Cosine of 30, you're looking at the long side in a 30/60. 3 over 2. Sine 45. Good. And sine 30, 1/2. Put it all together, and what do you get?
Square root of 6 plus square root of 4.
Okay. Let's try the other one. Let's see if it's more work, less work, same amount of work. It's the square root of 1 plus the cosine of 30 over 2. Okay, so cosine 15. So it's cosine of 30 over 2. 1 plus the cosine of 30 over 2. 1 plus cosine 30 over 2. Well, one thing is it doesn't require us to know anything about sine, where the formula up above did. This one just has just cosine. And the cosine of 30, we just did that up above. What did we get?
Square root of 3 over 2.
Square root of 3 over 2. So we have 1 plus square root 3 over 2 over 2. So the question is going to be, is that the same as square root 6 plus square root 2 over 4? Okay. Well, that's kind of a mess. Let's simplify that. You're dividing each one of these by 2. What's 1 divided by 2? Okay, so we got 1/2. What's square root 3 over 2 divided by 2?
Square root 3 over 4.
Okay. So I'm just going to keep changing this, manipulating it until maybe I get what's up above. What would I have to do if I want to add those together? I need a common denominator, which would be?
2 over 4.
So common denominator would be 4, which is the same denominator I have here. So this is looking good. All right, so denominator of 4. What would we need to do to change this to a 4? Times 2 times 2. All right, so I'm going to end up with 2/4 plus root 3 over 4. Okay. When you want to take the square root of a fraction, how do you do it? How do you take the square root of a fraction? Yeah. Yeah, take the square root of the numerator and the denominator. So you'd have the square root of 2 plus root 3. You got to fix that. You can't have a square root and a square root. That's a mess. Over the square root of 4, which is 2. All right. How can we fix having a square root and a square root?
Multiply by square. What? Sorry, I thought you were doing a fraction with the square root of the
You square it so that it's 2 plus square root of 3, and it's not in a square root, and then
Can't we just?
But 2 different powers.
Well, if you square it, is that going to still be the same answer? Like if your answer to your problem was supposed to be 5, and you just square it, do you still have the same answer?
no.
No. If you had an equation, you can square both sides, but we don't have an equation. We just have a number here. The goal is we got to figure out how that number is supposed to be that number. Any thoughts on that? Yeah?
Multiply the time or multiply by 1 over that number or something like that, like multiply by 0.
You can multiply the top and the bottom by the same thing. What are you thinking of multiplying the top and the bottom by?
I don't know, somehow I thought about like putting 2 plus the square root of 3 on the bottom, and then you like have to flip it because then that gives you 6.
Well, what you could do, I mean, you can do this. You can multiply the top and bottom by 2 plus the square root of 2 plus the square root of 3. I know it's going to, but then that's going to put a square root in the bottom. So now I've just moved my problem from the top to the bottom. So that's not going to work nicely. Any other ideas? There has to be a way somehow to make that look like that.
Just like multiply it by 2.
Multiply the top and the bottom by 2.
Yeah, 2 over 2.
You can do that. I mean, that at least makes the bottom a 4, which is what you want. So at least you made the bottom match. So now you have 2 square root 2 plus root 3 over 4. Multiply the top and bottom by 2.
By putting the 2 into the mark.
So now, since the bottom is good, the goal is how do you make this
Well, 2 is like
look like this?
2 is like 2 on 2 squared. So like if you had 2 squared in the square root column, only 2 would get out. So can you apply the 2 to the stuff in there, like separate the 2 and the square root of 3 and apply?
What you'd get if you tried to bring the 2 under is 8 plus 2 square root of 3.
And then you can apply the 2 to the square root of 3.
You trying to bring that 2 back inside?
Yes.
Okay. I gotta think about that. So when you bring a 2 back inside, what
It's
would
2
it have?
times 2.
4
It
squared.
would have been a 4. So yeah.
Yeah.
You have,
Plus 4. Plus.
you'd have 8 plus
All right, let's try it.
square
So
root.
that would hold on, big brain can't think. So yeah, we got the 4. So you're talking about like this.
I thought it would be like plus 4.
No, it's
Mm.
times 4.
Because if you brought something out and it became a 2 and it was a square root, it would have had to have been a 4 on the inside.
Oh.
So you can definitely do that. That's okay.
You now have
But I'm still not sure exactly how that's going to lead us to.
8 plus 4. 8 plus square root of, like, yeah. Then can you put the 4 back into the 3?
that would bring it
Yeah.
up to
Yes, you could.
16.
And then could you separate the square root to, like,
Hold on, let me think for a second. So yeah, if you put that 4 back in, it
Yeah.
would have had to have been a 16. So that would have been square root of 16.
Times 3, and it would be equal to 48.
and then the way that you separate the square root is that you have 2, like if I multiply square root of 4 times square root of 4, would that be square root of 4 plus 4? What's the relationship for square roots? Like, how do you combine them or separate them?
Well, you can factor it into 2 numbers, but that would take us back the way we came. I mean, anything we're doing is good. I'm just not sure how to get there because I never tried to.
So what happens if you multiply square root of 4 by square root of 4 in a separate problem?
Square root of 4 times square root of 4.
Yeah.
That's the square root of 16.
But it would be the square root of 4 times 4. So how do you do additions? How do you, like, is there a way to, like, separate addition in square roots?
No, not that I know of. No. Yeah.
So we take the original, like where we had square root of 2 plus square root of 3, and would we do,
Right here.
yeah, no, above,
Here.
no, the original one. Can you, so you can't like do like the square root of 2 over 2 plus like the square root.
Yeah. If you have something like this, you can't do this if that's what you're asking. You can't take the square root of each number separate. That doesn't work. So I have to think a little more about that. It might be something obvious that we're missing, but there must be a way to somehow make that look like that.
Square root of 48 is around 7, but, like, it's not 7 exactly.
It's 1 below it.
Yeah, I'm just curious with everything we've done, if we still have the same thing. Let's just see what the square root of 6 plus the square root of 2 is. And let's see if it's the same as all the work we've done. If it is, then we haven't messed anything up, we just haven't figured out how to do it.
Us to follow with the square root idea because, like, the answer has, like, them separated, so I was wondering how we separate them.
8, what is it? 8 plus square root of 48. So whatever we've done so far, everything is right. We haven't made any mistakes because the numerators are still equivalent. I'm just still not sure how do we rewrite it to make it look like the other one. I'm gonna have to think about that a little more. But everything we've done is we didn't make any mistakes.
Yeah.
So that's the homework for tonight. I'll take a look at that problem and see if I can figure out something simple. And then tomorrow we'll do section 76.